This video we're going to rederive the expression for logistic regression, but we're going to, instead of just specifying an error function by fiat, we're going to use a technique called the technique of maximum likelihood. So this is a kind of backward inference that sort of discovers the most likely cause for some observed event. And so metaphor that we used in class was if you have a dark room and you know that inside the dark room there is either a candle, a bunny rabbit, or a mountain lion, and your friend goes into this room and then comes out screaming, you can find the possible contents in the room that maximize the probability of seeing what you actually saw. So if there was a candle in the room, what's the probability that somebody would run out screaming? Low. If there was a bunny in the room, what's the probability that someone would run out screaming? Depends on the person. Medium? I don't know. But if there's a mountain lion in the room, the probability that someone would run out screaming is high. So the thing that could be in the room that maximizes the likelihood of what you actually observed is the parameter set that is the solution to the maximum likelihood set of equations. So now we're basically going to do all that with calculus in the context of logistic regression. So remember that the whole idea of logistic regression is that, sorry, I'm going to get on this page here, it's blowing my mind. The whole idea of logistic regression is that theta of WTX is supposed to approximately be equal to the conditional probability of the label Y equals 1. So this is probability that the classification is in the positive sort. This is binary classification, given the instance. Okay, so now if you take this seriously, so in the very first video here, we showed kind of how there's two things sort of give you the data set that you actually see. There's a probability distribution on the instances, and that tells you sort of which x's come along. And then there's the conditional probability on labels that assign labels here. So this is sort of like a coin toss, but it's not necessarily a fair coin. So this could be like a 90% probability for some of these, and it could be a 20% probability for others. So for each instance that is generated by this probability distribution, you sort of flip an unfair coin according to this probability distribution to decide whether the label is +1 or -1. So here this is sort of, God's function. Nobody knows exactly what that is. So we can regard W as being the thing that causes the labels to come out. So regard some unknown W as being sort of the secret cause of the labels that we actually see when we look at the data we have. So some W's will be more likely than others. For instance, if these are all 0 and you're considering a W that always makes this a value that's close to 1. I'm sorry, I forgot we're working with plus and minus 1. If these are all -1 and you have a W that always produces a dot product here that's close to 1 on the x's that you have, the likelihood that that W caused this data to be observed is small, right? So what's the probability that we see the data that we see, the probability that we see the labels that we see? So we model the data generation process as being a bunch of independent, identically distributed draws according to this process that I was just talking about. And because of that independence, the probability that you see the labels that you actually see is the probability of it's just the product of the conditional probabilities of all the data points that you actually do have. So because of this assumption that theta of this dot product is a model for this expression, what we have here, so remember this, we derived this last time. So the probability, so here this is the probability that y is equal to plus 1, right? And it turns out that the probability of just y given x is equal to theta of y times WTX. Why is that true? Go back and watch the first video in this playlist and it does that derivation. So I'm just going to use that fact here. So what I have is the product of theta yi times WT xi. And so now what we do in the maximum likelihood method is just to find the W that maximizes this. Okay. So this is a product of probabilities, and some of them might be quite small, you know. So imagine that you have 1,000 data points, and some of these probabilities are like 1 in a million. When you raise, 1 over a million to the 1,000th power, you get something that is too small to be represented in computer memory. So you end up with these problems of like a numerical loss. Which we don't want because we're going to use a numerical approximation technique to maximize this thing anyway. So rather than maximizing this, we're going to dress it up a little bit. So I'm going to multiply a factor of 1 over n. So n is just the number of data points. And I'm also going to I'm going to introduce a negative sign here. And I'm going to apply natural log to the whole thing. Okay. So this is a common trick when you might have seen it before when you have a product of probabilities. Often you work with the logarithm because the log will turn. First, it'll take small numbers and make them big in magnitude, which is good. But also it turns the product into a sum, and the sum of 1 over a million 1,000 times is no problem. So let's think about what we've done here. So natural log is an increasing function. When you make it negative, that's a decreasing function, and we've wrapped it around this. So suppose we have the W that makes this as big as possible. That'll make the input to this expression as big as possible. Which will make the output as small as possible. So now, rather than maximizing this, we are going to minimize this. And these two things are equivalent. So the W that minimizes this is the same as the W that maximizes that for the reason that I just explained. So now we're going to do some algebraic massaging here. So this is minus 1 over n. Natural log turns the product into a sum. And this becomes natural log of theta yi wt x. Okay. Now there's a negative sign here, so I'm going to push it in. And this becomes 1 over n of natural log of 1 over, this is very similar to a derivation that we did, I think in the first slides, maybe the second slides. Why am I saying slides? They're videos. I forgot to put the I here. I also forgot to put the I there. There it is. Okay, so remember what theta is. So this is 1 over 1 plus e to the minus s. Here I'm taking its reciprocal. Why am I doing that? That's because the minus 1 power got pushed in. Minus 1 power means reciprocate. So if you reciprocate that, obviously you get what I'm about to write. 1 over n times the sum of natural log of 1 plus e to the minus yi wt xi. Okay, and so what you'll recognize here is this is just soft plus of minus y I w t xi. So in other words, it's just the pointwise error function that we have been talking about this whole time. And what are we doing with it? We're just taking the average. So this is just the average of the pointwise errors. And so this is the error, the n-sample error of the weight vector W on the whole data set that we have. So now how do we actually, I guess now we want to find the W that minimizes this, right? So we use our calculus techniques. So basically we take the derivative and set it equal to 0 and solve. So what is the derivative of this thing, or the gradient? It's going to be equal to 1 over n, and then you can ignore the sum. And then this is natural log, so it becomes, I'm getting ahead of myself here. So on the bottom, you write 1 plus, this is just the way you normally take the derivative of natural log if you have had calculus 1. And now what you write on top is the derivative of the bottom, so that's e to the minus yi wt xi, and now finally you write the derivative of the expression, but what we're writing is the gradient of the expression, which is minus yi xi. Okay, and you can simplify this a little bit more, because another way to write the logit function is like this. So that's similar to what we have here. So this is another way to write what we have here is logit of minus yi wt xi, and there's a minus sign. I'll write it out here. There's the negative sign, and yi times xi. So that's the gradient, and now you have an expression that you can use to do not stochastic gradient descent, but full batch gradient descent if you want to. Or you could only use some of the summands, like a randomly selected subset, and do mini batch gradient descent. So we've just kind of re-derived everything. Or if you want to, you could just regard this as the average of those, and then use that as your pointwise, the gradient of your pointwise error function, and use stochastic gradient descent. Okay, so I've made the point I wanted to make, and we're gonna give you a quick look here. Hold on. How's it going? Now I'm gonna stop the video.